Welcome to Ones and Zeros. My name's Ben, and today we're going to be taking another look at FPGAs. So we're going to be doing the second video in our FPGA basic series. And today we're going to be following on from the last video and looking at another rather important but quite basic part of FPGAs, which is registers. So whereas in the last video we looked at some of the basics as far as hooking up inputs and outputs, things like that, that's super important for getting data into and out of the FPGA, but we're also going to need a way to be able to store bits of data that we're working on, or things like particular settings for how the hardware we're working on is going to operate, or status registers, things like that. So you might be familiar with that concept if you've had a bit of experience working with microcontrollers or even computers, where you'll have CPU registers that are used for storing temporary values that are being worked on, or for putting hardware or a CPU in particular modes, things like that, or for storing the status of a CPU or a particular piece of like a hardware peripheral in a microcontroller, things like that. So that's quite an important thing. And we're going to have a bit of a look at sort of the basics of how we can go about actually using that sort of thing in today's video. In the next video, we're going to start to look at things like clocks and stuff like that, and sort of build up a whole bunch of different basic things. And in terms of data storage, of course, there is different approaches to storing data depending on what you're doing with it. So there is things where data is stored in arrays like RAM and ROM, things like that as well. But in its most simplest form, a register is a little bit of memory used to store one particular value containing a certain amount of binary bits. So going to take a bit of a similar approach as we did during the last video, where we're going to be using the Thoracic D0CV board, which is this one right here, which we've got sitting there ready to go. And we're going to be making use of the switches and the LEDs like we did previously. So we've got 10 switches and 10 LEDs there that we can play with. And along with the push buttons to sort of control how we're actually going about storing a bit of data as well. So in this case, we're going to be storing 10-bit values in a particular register due to the fact that we've got 10 switches and 10 LEDs. So that kind of fits. Well, typically you might be storing, say, an 8-bit, 16-bit, 32-bit, or 64-bit value to go with sort of a more traditional approach. But with an FPGA, we're not limited specifically to that, and we can have an arbitrary number of bits if we would like to. So we'll switch over to our screen there, and we do have our Quartus Prime Lite edition set up fairly similarly to what we did in the last video. If you'd like to know how we go about actually getting to this point, I might do a video specifically just on the setup part, but we've also included that in the previous video too. How I go about sort of simplifying things and getting rid of a few bits of fluff and stuff like that that we don't need when we're just messing with some of the basics. So all we've got at the moment is basically just our inputs and outputs being defined for the different hardware we've got. So our clocks, our GPIOs, our 4 push buttons, which are labeled key, our 10 LEDs, our 10 switches, and then stuff like our 7-segment display, PS2 VGA, SD card, and our RAM. As I mentioned though, we're basically going to be focusing on these 3 today, which is our push buttons or our keys, our LEDs, and our switches, and then seeing how we can use those to allow us to store a bit of data in a register. So first things first is we need a register to be able to store data into. So the way we go about defining that with our Verilog HDL is reg for register. We're telling it that we want 10 bits, so from bit 9 through to bit 0 in the square brackets there. We're just going to call this LED register because we're going to be outputting it to the LEDs. And we're just going to fill it with a default value or a boot up value, which is just going to be all zeros. So we're telling it we want a 10-bit hexadecimal value and all zeros for that. We could also put in a binary value like that, but of course we have to put in more numbers there in order to make up all of our binary digits. So in that case, it is a little easier just to put in hex. We could also go with decimal, although I typically prefer myself working with hexadecimal or binary in this case, but you could simply go equals 0 if you'd like to as well. That would also work. So we'll go with our hexadecimal 10-bit 0 for our default value. And then what we're going to do is tell it that anything that's being stored in the register, we want to be outputting to our 10 LEDs. So the way we go about doing that is tell it we want to assign to LED R, which is the name for our LED outputs. So assign to LED R equals LED register, which is pretty simple. It means anything that's in the LED register is automatically going to get output to the LEDs. And if we compile and put this on the board at the moment, we'll find that there's no LEDs lighting up, which of course, because we've put values of zeros in here, that's what we should expect. If we were to put in, for example, that'll be 3FF for all ones in hexadecimal for our 10 bits, then we should find that if we compile this and put this on the board, then we should get all the LEDs lighting up. So we can try that as a bit of an example. So we'll tell it we want to compile that just to make sure that that is all connecting up correctly and working. And then we're going to go through and look at a couple of different ways we can sort of store values into the register and manipulate those values that are in the register as well once we've gone through this bit. So just a matter of waiting for it to finish compiling there for us. This is where having a decently powerful computer can be really handy, but just to make sure that everything is streaming correctly, I do have it only using half of the cores that are in this laptop, so it's a little bit slower than it could be, but that way the computer's got a bit of CPU to handle the encoding and streaming and stuff like that as well, so we don't run into any glitches or anything there. And it's nearly done going through the assembler stage at the moment. Doing a quick bit of timing analysis just to make sure that it's going to meet the performance characteristics we're looking for, which doesn't really matter in this case because we're not really using clocks at the moment. And we are compiled. So let's go ahead and we'll get this popped onto the board. We'll make sure it's got the correct programmer selected, which it does. It's got our inbuilt USB blaster that's on the Thoracic board. I'm going to add a file to this and go into our output files, and we're going to grab our SOF file there. And it's all good. We'll click start on that to dump that over onto our board. So that's just popping it over there now. And if we jump over to the board, we can see all of our LEDs are lit up because we stored all ones for the bits in the register. So that lets us know that that is actually working correctly. So let's go through and actually get some ways of actually putting data into the registers. So jump back to our code. And what we're going to do is have it so that one of the keys that we're using will actually trigger the register to actually latch data. So essentially it's going to act as a clock, but it's going to be a manual clock because it's going to be one that's triggered whenever we push the button, essentially. We also want it to be able to trigger in a situation where we press the reset button that's on the board as well. Just so that if we want to restore it back to a default value in the register, then we can make that work as well. Just get that set up so that we'll be able to see the reset button once we switch back to the board. So the way we go about doing this is tell it always at the negative edge of key 0, and we'll pop in a begin and an end. So what this always statement is doing is basically telling it that any time key 0, so push button 0, goes from a high state to a low state, or a binary 1 to a binary 0, then it's going to do whatever is in here. So that will allow us to trigger the register to do something anytime in that statement, or we could put any number of different things in that statement to happen when that particular event occurs. In this case, we're not just going to have it trigger on that particular key though, because like I said, we also want to use the reset button. So we're going to go or negative edge equals reset n. And if we go up the top here, we can see that our reset button is connected to our reset n input. And that is a low active signal. So it means that it's normally high or normally a binary 1. But when we push the button, it will go low. So that means that we're triggering it on the negative edge or on the falling edge of the reset button, much as we're triggering it on the negative edge or the falling edge of key 0. So inside there, we're first going to handle what happens when we push the reset button. I always like to do that part first, just because it's kind of important. So we're going to say when, or if reset n is low, so if not reset n, which is what the means with the little squiggly, the tilde in front of it, then we're going to fill our register with zeros. So LED register, and in this case, to do an assignment, we have to put the less than symbol and then the equals to get it to store something into the register. And we're just going to go like that. So if it's detecting that the reset button's being pushed, regardless of anything else that's happening, and it's been triggered on the edge when we've pushed the button, then it'll fill it with zeros. And we're going to change our default value up the top here to all zeros as well. So we basically want the register to be empty when we first set it up or when we push the reset button. So that will handle the reset state for us. And then I'm going to go else if, well, actually, we'll just go else for the moment. And in this case, so if we're not resetting it and we've just pressed key 0, then what we might get it to do is just store the values from the 10 switches into the register, which will then be displayed onto our 10 LEDs. So for that one, we can just go LED register, and again, do our assignment with our less than and our equals. And then we're just going to go SW, which is the 10 inputs for our switches. And it's automatically going to assign those 10 bits from our 10 switches to the 10 bits of our register. Now, rather than compiling that now, because it does take a little while to compile, we might add a little bit of additional complexity to this now before we test it, and then we'll go and add some more stuff to it beyond that as well. But we might do something similar to what we did in the last video, where we might have it so that if we're also holding down key 1 when we press key 0, then it might invert the signals from the switches. Whereas if we're not holding key 1 and we just press key 0, then it'll just load them directly as is. So just so that we can see how that works there as well. So we're just going to go if key 1, then we're going to load in just the data from the switches into the register without manipulating it. Else LED register equals, again, the tilde symbol to invert it, and our SW for our 10 switches, like so. So that allows us to either load the switches as they are or the inverted copy of those switches. Gives us a little bit more to play around with so we can sort of see how that works. So we'll save that and compile that. and give that a bit of a test, and then we're going to go through and actually look at sort of how we can go about adding a little bit of maths to our register as well, so that we can get it to actually increment and decrement based on the fact that we've got two other buttons that we can use. So we'll make it so that if we're pressing one button and we press key 0, then it'll increment. If we do it with another button, then it will decrement, just so that we can kind of see how that works as well. So again, just going through and it's currently doing the fitter stage, so it's figuring out how to put what we're describing to it we want to happen into the actual hardware of the FPGA. And we will actually go through near the end of the video and actually have a look at how it's actually going through and making the FPGA reconfigure to become that particular hardware as well, similar to what we showed in the previous video. And also things like the particular logic diagram that it's coming up with to show how the code is being turned into an actual piece of logic circuitry effectively. So that's all compiled. We'll pull up our programmer. Again, we'll just go add file, we'll grab our SOF file, and we'll put that onto the board. Jump over to the board there now, and what we couldn't see before is this little button down here, which is actually the reset button itself. So that one looks like it has loaded, and we've currently got none of the LEDs lit up, so it has actually gone with the default value there. If we turn some of the switches on, so we'll turn these 3 on at the end, and then we'll skip one and turn a couple more on. And then if we press key 0, we can see it's actually loading that in there. And we have this end switch is also turned on at the moment, which is why that one's been turned on. So when we've pressed that, it's gone through and it's actually loaded that value into the register for us. So if we press or hold down key 1 and then press key 0, it should load the inverted copy like so. So we can see that the LEDs that were on are now off, and the ones that were off are now on. And again, if we press it without holding down key 1, we get the lights coming on the way the switches are. If we hold down key 1, we get our inverted copy. And then if we hit our reset button, then it resets the register back to all zeros. So that's kind of how that part works. So as far as actually loading values into the register, so let's get it doing something a little bit more advanced again and see how we go about adding a little bit more functionality to that as well. So we'll close that one there, and then we're just going to, might help if we type that correctly. I'm just going to go else if, and we might go key number 3 for this one. So if not key 3, and the keys, as I mentioned, they're all active low, so that's why we put the little invert in front of these, as otherwise it'd be triggering when we're not pressing the key rather than when we are pressing it. So I'm going to do that one, and then we'll also do one for key 2 like so. Now, depending on the sort of setup of the particular development board that you're using with your FPGA, it might have active high buttons, which means that you might need to go without the little inversion symbol. That just kind of depends on the way the circuitry is set up for that. In this case, though, as I mentioned, they're active low. So in this case, if we're holding down key 3 and we press key 0 to load the register, we might get it to actually increment the register. So it's going to treat the register as if it's a binary number, and it's going to add 1 to it. So in this case, we're just going to go LED register equals assignment LED register plus 1, like so. And then if we're doing key number 2 and we press key 0, then we're going to decrement. And again, fairly similar, we're just going to go minus like that. So as we can see, doing simple maths is quite simple in this case, and we could have whatever value we like in here. As long as it's a 10-bit value, it will still go through and actually add it in this case because we're doing the addition, or subtract it in this case because we're doing the subtraction. So, and the beauty of that is we just tell it that that's what we want it to do. It figures out the logic to actually make that occur, which is really quite convenient. So again, we'll go through and compile that, and we'll have a bit of a look at how that works, and then we'll go through and have a bit of a look at what it's actually doing as far as the actual logic circuit diagram that it's developing in order to make that functionality happen based on what we've described to it. And we'll also see sort of how it's making use of the particular resources on the FPGA itself as well. So, and again, because we're doing something fairly similar, not much more complex than what we were doing in the last video, we'll see that out of all of the resources available in the FPGA, we're going to be using very little. So it does leave us a lot of flexibility for adding huge amounts of functionality moving forward. And through the course of these FPGA basics videos, we're going to look at a whole bunch of different basic elements, and then we'll also be doing a video series where we start to put together some of the more basic pieces and start to do things a little bit more complex, like building hardware peripherals and things like that, all the way up to looking at designing a custom CPU with our own custom developed instruction set and things like that, so that we can see how those pieces go together to actually build a system that's capable of processing information based on a set of instructions. So again, that's all compiled. So we're going to go through and we'll add our SOF file to that one, and we'll get that to pop that on the board, jump over to the board there, and that's all programmed. So what we might do is we might just load up a binary 1 like so we can see just the first LED is set based on the switches. We just loaded that in, and again we could load in the inverse of that if we wanted to as well by holding down key 1 when we press key 0, or we can just press key 0 on its own to just give us the 1 there. So if we hold down key 3, which should allow us to increment the register by 1, every time we press key 0, it's going to perform that increment. So doing that addition for us, and as we can see, it's counting up in binary. And then if we hold down key 2, then every time we press key 0, it's going to decrement that register by 1, as we can see there. And it will actually roll over, as we can see. So it's gone from 0 all the way through to where all of the bits are set, so the highest possible value we can fit into that 10-bit register. And again, if we count back up, we'll see that it rolls over from this with all the bits set to all of the bits cleared, like so. And again, we still have all of the functionality that we had before, where we can get some of those switches turned on, load in that particular value. We've got our reset, and we can also load in our inverse value like that. So that's a bit of an example of how we go about actually using a register in an FPGA. And there's something that is, along with our inputs and outputs we looked in the last video, and along with the clocks that we'll be looking at in the next video, probably the most key parts to actually getting clocked logic working in an FPGA. You don't necessarily need clocks to be able to implement a bunch of different things, but for a lot of the sort of things that we're going to be looking at, there will be clocks involved for a certain bit of it, so that things will be happening at a particular rate, things like that. So let's jump back to our, not that one, we want that one. We'll jump back to this one, and so we can see what we've described there. We can see, based on what we just saw playing with the board, how it actually functions. Let's have a look at sort of what it's doing to make that happen on the FPGA. So firstly, if we go into our RTL viewer, we can see this is the logic diagram that it's created in order to make that functionality work. So we can see the register over here. We can see that it's got 10 bits, and that's connected directly to our LEDs. We can see our switches coming in here. Our first multiplexer, which is allowing us to select between either just the normal switches or the inverted switches. And then that's then feeding through these other couple of multiplexers. If we've got this one selected, which is connected to, is that key 2? So that's our decrement multiplexer. Then it's actually going to be adding -1 to that. And we can see that it's not actually doing a subtraction, it's actually adding the hexadecimal value 7FD to that. So if we zoom in a little bit there, we can see that a bit better. So by adding 7FD to whatever value is currently stored in the register, that is exactly the same behavior as actually doing a subtraction of 1. Things might work a little bit differently when we start working with what are known as 2's complement numbers and things like that. However, in this particular situation, because we're dealing with a number that's not positive or negative, it's just a positive whole number, that's the approach that it will take, because it's actually quicker for it to be able to do it that way. That's the most efficient way that the compiler has found to make that happen. So we can see it's taking the output of our registers here along this particular line as one of the inputs to our adder, and then the constant 7FD in hex is the second value that goes into that. And then it does have a carry input as well, which can be used, but it's just setting that to 0 because we're not actually using that. Now our next adder, so is this one here, which is the one that's actually adding 1. And that's going through this particular multiplexer, which is hooked up to key 3, which is what the 3 means here, as opposed to the 2 there, or the 1 over here. You kind of get used to reading these diagrams after you've had a little bit of practice with them. We can see that, again, it's taking the output of the register, going along this particular line. That's going in as our A input to this adder, and then we've got a constant of 1, which is being added to that. Again, 0 for our carry input because we're not using that. And then that output's going through the multiplexer. So through the set of multiplexers, it allows it to select what we're actually doing depending on which buttons we're holding down. And that sort of gives us a bit of an idea of how that's actually going about working. And using this particular view, especially once things start to get a little bit more complicated, is really beneficial, because you can actually go through and see, is what we're describing using the language actually being translated into what we want to happen, or has the compiler found something that it thinks might be unnecessary or whatever because we haven't coded it properly, and is it missing from our logic diagram, things like that. Now looking over at our register, we can see we have a couple of different inputs here. We can see coming in here to our clock input is our key 0, and that is what's actually triggering it to load the data coming into the D or data input. We've got a S clear input, which is got all zeros coming into it, so 10 bits worth of zeros, because that's the default value that we want to be using. And then rather than it hooking up the reset button to our actual clock input, it's realized based on what we've described that that is actually a reset signal. So it's actually connected our reset N signal here up to our clear N right here. Now there's other ways that we could approach the way it's actually going about doing this as well, but this approach works quite well, and it's understood what we're trying to achieve and wired things up in a way that suits the particular task that we're giving it. So it's really quite clever at determining sort of some of the best approach to making it work the way it needs to. So that's our logic view. And if we go back through and let's see if we can find our compilation report, wherever that's hiding. Somewhere in here. There we go. So in our processing menu, we can see as far as our logic utilization in the FPGA itself, we've got 18,000 or 18,500 adaptive logic modules. It's using 11 of them. So we're barely using any of the resources in there. We're only using 10 registers, so one for each of the bits in our overall register. And then we can see we're not using any of our memory bits or our DSP blocks or anything like that. So again, still got a huge amount of resources that we can actually play with, considering that we're just doing something quite simple. And we can see how that's actually being laid out on the chip itself. If we jump into our chip planner, wait for that one to load up, we can see how it's going about actually assigning resources. And the light blue blocks are the adaptive logic module blocks. And we can see down here, we've got some of them that are slightly darker than the others, which is telling us that those are ones that actually have resources being used in them. So if we zoom in, this one here, let's open this up. We can see what have we got? 2, 4, 6, 8, 10. So these smaller blocks in this row here will be the 10 registers that are being used to store the 10 individual bits of data. If we go into one of these guys, we can see in the diagram here, so this section over on the right hand side, each adaptive logic module contains 4 registers. In this case, it's using 2 registers, this one here and this one here, and each of those are storing 1 bit of our 10-bit number. And then it's setting up the logic using the lookup tables and multiplexers over on the left-hand side in order to give us the functionality that we want. So we'll close that one. So we can see that's where the data is actually being stored in those blocks. And then we can see where it's colored in all of these blocks on the left and these couple over here, as well as, where's the other one? Up here. These are the guys that will be being used to provide the logic for our addition and our subtraction, to do our increment and decrement, as well as the multiplexing of the keys in order to select whether we're wanting to invert the value coming in from our switches or whether we want it to increment the value or decrement the value that's in the register. So don't need to worry about that stuff too much. I do find it kind of fascinating though to have a bit of a look at how it actually goes about wiring up the FPGA to become the physical hardware that we want based on assigning the various resources. So I just thought we'd have a bit of a look at that as well. So that's kind of a bit of a simple look at what a register is in terms of an FPGA and how we can go about using it and storing data in it, manipulating data that's in it, and getting data out of it so that we can do something with it, in this case displaying it on the LEDs. So as I mentioned, next video in this series we're going to be looking at doing a bit of a look at clocks and how clocks can be used, and that kind of builds upon what we've done in this video as well. And then we'll start looking at other things like being able to use things like RAMs and ROMs, start to build certain blocks that are going to allow us to have the key pieces that we need to start doing more advanced stuff. So things like shift registers and FIFO buffers and all of that fun stuff, as well as being able to do, you know, parallel and serial input and output stuff like that that we might need if we're communicating via SPI or UART or things like that as well. So this series will just be looking at the basics, and then, as I mentioned, we'll be doing another series where we're starting to look at the more advanced stuff as well. So something there for everyone. If there's any questions or anything like that about what we've covered in this video, feel free to leave a comment. There is also other ways to get in touch with us as well. So if we jump over to this view, we've got down that corner there. You can jump onto our subreddit and ask questions there as well. I do keep an eye on that. Some of the more advanced code that we do with FPGAs will be going up onto GitHub. However, because this stuff's fairly simple, if you want to sort of follow along, do that based on the video. Some of the stuff we do in future will go up onto GitHub, so we've got the address for that one just down there as well. If you liked the video, we'd love it if you liked, and subscribe if you haven't already. We're definitely going to have a lot more cool stuff coming up looking at FPGAs. And if you want to help support the channel moving forward, help us to start to do more advanced things and delve into more in-depth projects and stuff like that, we do also have a Patreon as well. And we do also have up the top there, Craig, our first patron, who is the first person helping to build upon what we've been making with this channel as well. So thank you very much for that, Craig. And hope you all have a lovely day or evening, morning, night, whatever it is, wherever you are in your part of the world. And thank you for watching.